So yeah, it won't be 25 minutes. I just want to know after 20. Okay, so I'm very happy to talk here, and especially after Roberto, but because you'll see some connections between the two talks. Historians have argued that technological aims shaped post-World War II physics to an unprecedented degree. According to some, to the extent of a discontinuity with earlier practices of research. Stuart Leslie said, and you can see the quote, "Nothing in the pre-war experience fully prepared academic scientists and their institutions for the scale and scope of wartime mobilization that would transform the university, industry, and the federal government and their mutual interrelationships." Paul Foreman, in his work on post-Second World War quantum electronics, agrees with the physicist Gerald Zacharias, and he quotes Zacharias, "World War II was in many ways a watershed for American science and scientists. It changed the nature of what it means to do science and radically altered the relationship between science and government, the military, and industry." Indeed, the historical records do show that practical goals, especially of interest to the USA military-industrial complex, shaped much of Cold War physics, and that science, especially physics, formed a new alliance with military and the government. Since the USA dominated science at the post-war epoch, the experience there shaped science at large. Yet, the view that post-war physics experienced a new kind of applied research neglects the earlier strong influence of technological aims on physics. In other words, I think that in portraying the radical change in the relationship of science with the military and the government, historians assumed a too dramatic change in its relationship with practical applications. In this talk, I suggest that one significant change that coincided with the end of the Second World War was an expansion in the use of quantum mechanics in studying issues relevant for technology. A substantial part of interwar research dealt with subjects of practical interest, but quantum mechanics was marginal in those fields. It became a major theoretical basis for applications only during the 1940s. Moreover, I suggest that this turn from classical to quantum analysis in application-oriented study might have been a major reason for the historiographical exaggeration of the different applicative character of post-war physics in comparison to the interwar period and earlier ones. The thesis is rather speculative and needs further empirical corroboration. I hope to find part of the evidence and to revise part of my claim in my future planned research on the technological shaping of interwar physics. But as you know, the future is difficult to predict. The transformation of quantum mechanics into practical applicable theory followed two main developments. The first was the expansion of quantum theory into new fields relevant for technology, and mainly here the cases are cases of solid state physics. Semiconductors is one good example for that. Another case is physical fields and effects that had received quantum mechanical descriptions and they became useful for technology. Here the clear example is nuclear physics. As we know from the 1920s, physicists employed even the early 1920s, physicists employed quantum mechanics in probing into the structure and properties of the nuclei, until the discovery of fission, practical possible application were only marginal in the field. After the discovery, as you know, the practical application shaped much of the research in the field, as well as much of our political and world. The expansion of quantum mechanics and the turning of fields into applicable sometimes coincided. So if we look more closely on the case of semiconductors, it's also a case where physics quantum mechanics become more and more applicable and could explain more things in semiconducting, while at the same time semiconductors became more useful. So these both things are coming together. In order to illustrate my claim, I will review a few fields of interworld physics that were shaped by practical aims. That is, where a substantial part of the research were directed towards questions relevant for technological use. I will comment on the relevance of quantum mechanics to their study. The main attention will be given to the two central fields related to electronics, that is thermionics in the interworld period and semiconductors in the post-world period, but I will talk quite a lot about semiconductors already before the Second World War. The comparison between the two fields will help me illustrating my thesis. Okay. Applications did shape research in some fields of interworld physics, but quantum mechanics was not central in these studies. And especially it was not centered in those aspects related to the technological uses. The fields I'm referring to including the photo effects, the thermionics, which is the emanation of ions from hot metals, so electrons and other could be also, of course. Piezoelectricity, as you know, when I'm talking, usually I mention that. So it's the induction of electric polarity by changes of pressure, and optics, and, as mentioned, semiconductors. The famous external or outer photoelectric effect was basically well understood by quantum mechanical terms since Einstein 1905 famous work, an equation and accepted in the 20s. Yet that equation, Einstein's equation, was only the departure point for coming with terms with effects more interesting from a practical point of view. These were called internal or inner effects coming inside the material, and they were included latent stages in the process of absorbing of electrons and changes in the conductivity, which are called photoconductivity. These effects were complex from a theoretical point of view, but still extensively studied as they related to applications in detectors. You can see some of these detectors here, and these detectors were used for laboratory and commercial use. Commercial use are early facsimile and television. Remember, television was a very central research agenda in the 20s and 30s, more in the 20s actually. Companies like Kodak and Zeiss showed an interest in using the inner photoelectric effect for photography and for optical instrument. Quantum mechanics could hardly contribute to their understanding beyond the basic and important idea of light quantum and the connection between radiation and matter, but this was only, as I said, the first step. What one needed and what one used are phenomenological theory based on empirical data. Thermionics had the central technological importance due to its bearings on the incandescent lamp and the electronic valve. And these were the basics of the electronic valve, and especially the triode that you see here, which is the electronic valve with another grid in the middle, not always in the middle physically, were the basic of contemporary electronics. So until we have the transistors and well into the 50s, all electronics or most electronics is based on the triodes, and this is very important, especially for telecommunication, which you have just heard. That's one of the reasons that Bell Labs, when asked physicists to come to work there, and when they did what they did there was, even when it was applicable, it was physics. So that is very different from the financial companies today. They had to do physics related to these thermionics. And that was another, but the most famous early research in that actually was in General Electrics by Ivan Langmuir, and there was a similar work, and other very important works in Germany by Walter Schottky at Siemens. But the academy also was very interested in thermionics. Owen Richardson works in Cambridge, Princeton, back in Cambridge, Britain, suggested a few successive theories of the effect based on classical electron theory and later on thermodynamics. The effect received also a quantum mechanical treatment in the early 1930s. With the application of, since we have metals that emanate electron, there was the application of Fermi Dirac statistic to the gas electrons in the metal. Yet it continued to be treated mostly classically. One of the reasons was that the quantum-driven equation agreed with the thermodynamic one up to the value of the experimentally deduced parameter that you see here, A and B. And in this equation, I is the current, T is the temperature. And also, if you know that the differences in the numbers of A and B was not so important to in the cases that quantum mechanics could help, they were not so important in design of better thermionics valve. Quantum theory of thermionics was not motivated from a theoretical or experimental puzzles within the fields of thermionics, but from the effort to show that the applicability of the new foundation theory to many phenomena. And of course, personally, the ability of the particular theoretician that managed to solve that problem. It was, of course, very important, and that as often, always it is. Yet theoreticians work on other aspects of quantum mechanics. Young theoreticians worked on other aspects of quantum theory, developed the theory of for thermionics, and moved quite fast to other fields. This indicates that their main interest was in quantum mechanics rather than in thermionics. Quantum theories of physicists like Lothar Nordheim, who had the first important theory in 1929, and more elaborated theory was suggested by Wigner and Baradin. So these physicists, in 1935, these physicists could deduce, with proper assumptions, the properties of the electron emission from a clean surfaces. So if you have only one metal, and this is what they call the work function, which comes into the place of B in this equation. Yet, these theories could not account for more complex effects, and like in photoelectricity, the more complex effects were more interesting. So most research in the field concentrated on these more complex effects, like the emanation of electrons from oxide coated layers and from composite metals, where the quantum mechanics could not tell much about them. These questions were studied, therefore, in more empirical way and received theories specific for particular cases using little or no quantum mechanics. Competitive theories for oxide-coated metals, for example, were suggested around 1930. They relied on assumptions about the underlying interaction between metal and oxygen, but not on an elaborated quantum descriptions of the relationships. As with the photo effect, the more complex phenomena were also more interesting from the point of view of applications. It is thus not surprising that industrial physicists contribute much to the empirical and theoretical studies of these aspects of thermionics, working upon undergrad Bell Labs, but not only. And these aspects, as these aspects pertain to the central technologies of such big corporations like AT&T, General Electric, Siemens, and a few others. An example in which quantum theory had virtually no role, although in general one could think that it would be applicable, was piezoelectricity. The First World War turned piezoelectricity from pure to applied field more dramatically than the Second World War, who changed the study of semiconductors, albeit in a research field of much smaller scale and much lesser importance. I don't claim that there is any similarity in the importance. The piezoelectric effect became useful only during the war with the sonar for locating submarine. It became technologically and scientifically more important and interesting with Walter Cady's discovery of the stable, sharp electric resonance of crystals. You can see how this kind of very sharp resonance of the crystals, and this effect is still ubiquitous in frequency control and time measurements today, as it can be used for measuring frequency and time are the same, about the same. Subsequently, the research in the field dramatically expanded, and the central question changed to those of technological interest, such as the properties of the piezoelectric resonators and their dependence on other physical conditions like temperature. While the study was mostly empirical, it included also theories regarding the properties of the piezoelectric resonators. Most of these theories were classical phenomenological in character, based on classical elasticity and electrostatics. Even the few who attempt to connect the effect to the atomistic lattice structure, an effort which was not connected to practical aims, even these people did not apply quantum assumptions, while they did relate to other contemporary development like the knowledge coming from X-ray diffraction techniques. Actually, piezoelectricity also helped X-ray diffraction techniques to using the X-ray diffraction techniques. A nice example is that of Born's theory. Born was the one who employed a quantum assumption in the explanation of the properties of crystals in his lattice theory from the middle of the teens and then in the 20s. And he had a theory with two of his students who already mentioned here, Elizabeth Borman and then with Gustav Heckmann. And they had theories also of piezoelectricity, but the part deals with piezoelectricity like the parts dealing with electricity had no quantum assumption whatsoever. Semiconductors suggest a more complex example, which shows us also the increasing relevance of quantum mechanics for a field of technological importance. In the interwar, electronic semiconductors played at best a secondary role to that of the electronic valve, or thermionics. Still, they were used as a current rectifier, the use of copper oxide and selenium, and raised hopes for future replacement of the bigger and, what is very important, hotter valves. So the idea that we could change the valve to another thing was something that people thought of. The properties of semiconductors were not well understood, however. Quantum mechanics did not suggest a general scheme for their understanding. Even their mere existence as a genuine kind was contested until the mid-1930s. There is a famous quote by Pauli that we wrote to Peerless, famous in, you find it in some place in the secondary literature. So he wrote Peerless in 1931, one shouldn't work on semiconductors. That is a filthy mess. You can have the German is better. Who knows whether any semiconductor exists? Still, during the 1930s, some physicists did not adopt Pauli's suggestion and apply concepts from quantum mechanics like holes, holes was the most important of them, to account for particular effects in semiconductors. These effects receive separated explanation for what in retrospect seem as different products of what later is called minority carriers. A more comprehensive understanding of semiconductors followed the development of the band theory of solids in the late 1920s and early 30s. This quantum mechanics theory was developed to answer puzzles in the theory of solids, both of metal and insulator, where different explanations or explanation of different phenomena did not agree. That's like the heat capacity and conductivity contradicted each other. As with the quantum theory of thermionics, which followed also the theory of solids, the wish to show the applicability of quantum mechanics to this realm was also a very important motivation for the theoreticians. The band theory allowed a new quantum mechanic-based understanding of semiconductors as different from both conductors and isolators. During the second half of the 1930s, a few competing theories of semiconductors were developed and made them as something separated. Among others, there were theories, or bunch of related theory by Schottky, Mott, and Davidov. They are separated. And there were other band of theory by Wilson, and others which were based on tunneling. Tunneling is more problematic in retrospect. All based on but all of them based on quantum mechanical concept with the idea of the band theory. By the outbreak of the war, semiconducting was experimentally and theoretically established field, even if many questions about it remained open. In the process of making semiconductor a viable scientific field and a basis for technological application, not less important than theory was the development of empirically based methods for manipulating the semiconductors, that is, in a method for producing useful effects with the crystals, and useful effects are needed in the laboratory and later for practical aims. This method included producing semiconductors with the desired impurities, which also it comes with the understanding that the impurities are important, that you need to know, not to have them too much impurities, but not too little also. And improve uses of semiconductor as rectifiers, mostly for high frequency waves in radar in the world. That was the most important motivation. And so in the early 1940s, or in mid-1940s, you had both pure semiconductors as you want and the knowledge how to use them for rectifiers. And this also accompanied with better theoretical understanding of the effect that you now have and can produce in the laboratory. The theoretical and empirical development led to expansion of research on semiconductors, and this began already at the eve of the Second World War. Expectation for possible future application motivate part of the research, and I'll give here the example from AT&T, which we just heard, and Roberto says that AT&T began recruiting experts in quantum mechanics only in 1936. This followed two things. One was the ease of the economic crisis, but more important for my interest here, in the 6 years that elapsed since the corporation had recruited scientists, quantum mechanics developed, and with it the expectation that quantum mechanics would be of practical implications and used for the corporation. The new theoretician explored various fields from magnetism to interactions between electromagnetic radiation and electrons, among which solid state formed the major cluster, and semiconductors a central subject. Still, researchers at Bell Labs examined also other questions related to solid state. For example, they looked also on thermionics, where quantum mechanics pertained to the properties of the metals and their work function. AT&T expanded in its research and quantum mechanics, research on quantum mechanics and semiconductors, in particular after the end of the war. A nice illustration for that is the requirement of John Barradine, which I mentioned him earlier with a theory on thermionics, and the establishment of a research program directed at the invention of solid-state amplifier. That became an attainable goal due to the above-mentioned development. While the program was stimulated from advancement made during the Second World War, it was rooted in a longer process stemming from the interwar periods. In other words, the effect of the late 1930s implementation of quantum mechanics at Bell Labs was felt only after the end of the war. Famously, the post-war research led to the invention of solid-state amplifier, the transistor. The invention transformed electronics, putting microelectronics at the fore, and quantum theory a key element in the research and development. The move from electron emission in vacuum to solid-state electronics was also a move from semi-classical theories to quantum mechanical ones. The work of Langmuir at General Electric on the one hand, and of Barradine Shockley at the Bell Labs on the other hand, is a good example for the move, because to advance in his works on a composite emitter, Langmuir in the teens and 20s deliberately ignored the advancement in quantum mechanics. They were irrelevant for him. Barradine, Breton, Shockley relied on quantum mechanics in the research and development of the transistor. While quantum mechanics was marginal in the study of the vacuum tube, it was central in the study of microelectronics. And as historians like Foreman showed, many physicists studied issues related to practical application in the field with the use of quantum mechanics, and this kind of technology shaped the related research in physics, and it led to the impression, which is quite justified, that considerable part of post-war physics were oriented towards applications. Microelectronics was far from the only field of industrial significance in which quantum theory became important. There were others like lasers. I won't go into that. Yet, research aimed at results valuable for technological application was not new in physics. The extent to which that research relied on methods and concepts from quantum mechanics was novel. The scope of research oriented toward practical ends were also new, but we should remember that the scale of research in physics in general was new. We saw it yesterday in one of the slides. I think Christians show us. Still, research oriented towards subject of interest to technology was well known in the interwar period and before. To return to quantum mechanics and to conclude. Almost from its formulation, theoreticians examined ways of extending quantum mechanics into further realms of physics, and think about the slides that Christian showed us yesterday of that. Most of its earlier domains of quantum mechanics, however, structures, atoms, and simple molecules, the nuclei, did not have clear technological applications. The interaction between radiation and matter was of a more practical application, but still limited use. Moreover, the use of quantum theory did not promise advancement in the technological applications of these phenomena. Yet, with time, quantum theory extended its domain to areas of more practical interest, most notably to solids, including semiconductors, and that will become at the late 1930s. Quantum mechanics became relevant also to other technological concerns, including some related to the electronic valve. The war research and the post-war atmosphere helped making the study of solids more practical and at the same time more strongly embedded in quantum theory. The strong connection between quantum mechanical treatment of microelectronics and the practical applications strengthened the impression of a new kind of alliance between research and technology, and in this sense, they overlooked previous non-quantum predecessors. Thank you.
All right, great. Yes, Alexa.
Shaul, I wonder if you have some kind of a solid-state arrogance versus spectroscopy, because spectroscopy and atomic spectroscopy probably also had some very useful practical applications in interwar. Let's say new sources of light, the bulbs, that, I mean, like neon lights, for example, and things like that. I mean, you don't need solid-state, but kind of just the study of atomic spectra. I mean, you may call it semi-classical possibly, but I'm almost sure that kind of people with quantum ideas will kind of looking into kind of applications of just kind of atomic spectroscopy into useful devices already in the 1930s, definitely.
I think the first thanks for this remark, because I didn't think much about that. I think my idea would be that probably there is not you didn't need a lot of theory there, but of course, but with the use of the experiments, and fluorescence, I think, was not so central but it began to be at the interwar period. So I think it should be examined. That's for sure. In a sense, I totally agree that physics was applied in the interwar period. So that would be my. That's in a sense my central claim, and it will be interesting to see how much quantum mechanics was used there in this field.
Yeah, Aaron.
So, I can see how this could be a great project. I'm curious about the historiographical piece you said at the beginning, and then what we see here. Do you want to argue something specifically about quantum mechanics and continuity pre and post-war? You know, of course, there are many examples of sort of interaction of government, science in general, right, and industry, and we can look at energy and empire for the 19th century British case, or more biology things for earlier sort of European, right? And I think that you probably can't contest that, you know, the experience for physicists pre and post-war in the United States in particular was different, where all of a sudden the government was not only saying, we have a problem and we'd like you to solve it, but also people were writing, you know, to John Wheeler saying, you know, hi, I'm from the military, I hear you're interested in gravity, and we fly things, so, you know, here's some money for your quantum gravity program, right? This had just not happened, right? So I'm curious whether you want to make an argument about sort of science, industry, government in general, just quantum, and then even more particularly where you're seeing the line of influence. Is it You know, the scientists coming up with an idea and presenting it to industry science, right? Or is it government or industry going to the physicists and saying, we have a problem, like, which is like the sort of the Manhattan Project sort of image, right?
Okay, thanks. I hope I will remember all the things. No. It's actually good because it allows me to elaborate. So, and to clarify, I totally agree that the relationship between science and the government and the military as part in the U.S. was totally new, and that, of course, there is a radical change there. That will be for that. I don't contest that part. Yeah. But Staley says also had also there the industry. Yeah. And I think that the relationship with industry were not radically changed. And what I would like to say, so when you put that, I say that it was the technological applications were very important already for physics before the Second World War, also before that, I don't and much of the research in different fields was shaped by these applications in mind. So that the fact that people studied mostly composite thermionic metals was because these were the ones that were more useful. So that in this sense, now the difference where quantum mechanics. So quantum mechanics, this is not at the center of my idea, but one of the things I try to see. Okay, why do people emphasize so much the change after the war? So there are various reasons. Part of them because there is a change, but part of them is that I think that one of the changes is the fact that the fields that became more, the quantum mechanics become more applied in the interwar period. In the afterwar period, I think that what we see in AT&T gives us hints that had the war did not come, it would have taken more time and it would have reached there. Okay, but that's of course totally speculative. So my interest is mostly in showing in showing these connections to industry, and that also relates to Roberto's talk. And then I think that when you look on what people did in industry, you can see that they did physics, but they did specific physics, and their colleagues in the academy often did things which are similar, also with the thought of the applications. So it did not. So I'm very much interested in what people did in general, not only in the industrial laboratories, but actually outside the industrial laboratory.
Christian.
Thanks. It was like very rich and very interesting talk. I want to press you on the periodization you used. So you used this periodization between classical, semi-classical, and full quantum mechanical. And this is something, for instance, that is done in this book, Out of the Crystal Maze on the History of Solid-State Physics. And I wonder whether this periodization is helpful. Because if you think, for instance, of applying Fermi-Dirac statistics, is that semi-classical because it was developed within the old quantum theory, or is that classical? Not at all. Is it quantum mechanical? Maybe. So it is like something that shades a bit the variety of approaches that people took, especially during the 1930s. If you call all of them semi-classical, it makes it appear as if you have like a semi-classical approach that is well-defined. And this is totally not the case, and I know that you know that. So this opportunistic attitude in applied physics and this greater variety actually led to many new interesting concepts, like for instance the band theory of solids and many other things. So this somehow volatility is ill-described, I would claim, by just calling it semi-classical, and I wonder whether you might want to comment on that.
Okay, first my thought is that I did follow the Out of the Crystal Maze with all its. I am aware of some of its defects, but and I think that what I'm thinking, where I would not think so much of the Fermi-Dirac statistics as semi-classical, but what I usually think about is that you use only one concept from the quantum theory to a scheme which is still classical. In this case, I would call it semi-classical, and this also sense that it means that you don't need to be very well trained in quantum mechanics to know to implement that, because of course those people who were, they too, and I think that in general physicists are opportunists, whatever, because they need to solve problems in this sense of opportunism, not in.
If you're solving Schreber, you think?
Yeah. Okay. It might has influenced me, but I think that in general they are quite opportunist in trying to solving problems. Now, of course, which kind of ways to solve is legitimate. It very much depends on the community.
So, just one sentence to follow up. I think this doesn't mean that they're lazy, right? But more along Jean-Philippe's lines yesterday, that somehow this is a very constructive thing to do, because you reach new concepts that way.
I think the argument and the question is when is it constructive, and when it makes things that only you get when it is constructive to get new concepts, and when it's only useful for your end. But usually you have a specific end.
Kenji.
Thank you, Shaul. Great talk. I really learned a lot. So my question is about, how can I say? So within the larger framework you presented at the beginning of the talk, the reason you looked at quantum mechanics is, of course, we are all interested in quantum mechanics, but the reason that the case of quantum mechanics is important is it because it's the main field in which research became more useful after the war? I mean, war. So is that the correct way to understand it?
So if I understand correctly your question, I think quantum mechanics. My emphasis here on quantum mechanics came from two reasons. First, this is a conference on quantum mechanics, so. And second is the fact that after the war, in the post-war period, really applied physics, central areas in which people of applied physics were quantum mechanical.
Oh.
But in the interwar period, I would claim the other way around, that most fields that were being used for and being influenced from technology and being applied were non-quantum fields.
See. Okay, I understand. So it's not just quantum mechanics became useful, it's more like applied physics became quantum mechanical.
Yes, to a large extent, yes, not totally. Of course, you'll find many optics works which are not, and also today many things. But yeah, or the dominant, quantum mechanics became the dominant field, the dominant in applied physics.
Thank you.
Lex.
Yeah, I just wanted to intervene with what Christian asked. My feeling that maybe a more proper term is not semi-classical but semi-theoretical. In a sense, it's not about the levels of theory. It's a level kind of what use of, let's say, quantum ideas people had who were not trained as theoretical physicists. They didn't do calculations according to quantum mechanics, but they were like quantum ideas adopted to experimentalists' work. Not like Shockley. Shockley was doing calculations according to quantum physics, but there were many people even kind of before Shockley who would be like knowledgeable something about quantum mechanics or quantum, and it didn't matter from this point of view whether it's old or new, but it's basically the way how, let's say, experimental physicists mastered quantum ideas and how they applied to their work. And I think this is where most of this work goes. Kind of, it's not. I mean, they would not necessarily do sophisticated calculations by themselves, not necessarily with the Schrödinger equation, but they would have certain grasp of what quantum ideas, quantum physics is, and that may come kind of from. So that's why I would call it semi-theoretical or kind of quantum mechanics for pedestrians.
Any further questions? Okay. Oh, Michel?
I can't resist this. I like this distinction, and I just anecdote occurred to me because I'm like, well, Shockley did do these theoretical calculations. Walter Bertin, of course, did not. And so there's a joke going around, like in Minnesota, by like one of our distinguished physicists, Ed Nye. So I heard this from Roger Stewart. So Ed Nye used to say that Walter Bertin was the stupidest Nobel laureate that he'd ever met.
All right. Any further questions? Okay, תודה רבה, שאול.
Okay, yeah. Okay, I need a couple of messages for you. Hi, the first one is to congratulate you for everything. It's not over yet, right? You have to do that. But we're getting there. No, there's one thing that I think Michel has been pressing me about 300 times in the last 3 days, saying this is a great conference, and these things shouldn't be missed, right? Or lost in the ether, you know, my topic. So anyway.
Cyberspace.
Yeah.
They moved to the cyberspace.
So you know it's being recorded, and as I said, I will ask each one of you before uploading it on the website of the conference. But also, I think it would be interesting, and Michel was saying that, it would be interesting if you so wish to send me your PowerPoint presentation so that when we upload the video recordings, I don't know what the quality will be like, so that we also have the PowerPoints uploaded on the website, on the... Well, that computer is, yeah, but that computer is kind of will be raised and disappear.
But we have ways of getting files from one computer to another.
Yeah, so yeah. I'd rather have them on an email or something that you send me, so that's a safe way to have it, if you so wish, right? And yeah, bon appetit for the lunch, and meet at 3 afterwards. Yeah.